Good morning, everyone, and welcome to PoDIUM's final webinar. Today's webinar is actually a wrap-up, PoDIUM in a capsule, as I say, and we're taking a step back, looking back in the future and in the past, and following the full PoDIUM journey since its beginning back in October 2022. Today we're looking into project results and then the road ahead, but we will highlight what we tested, what we learned, and what stood out from all three living labs of the project in Germany, Italy, Spain, and across the five different use cases that were tested and demonstrated. My name is Sevi Christoforou, and I'm a Communication and Dissemination Manager with ICCS. It's the coordinator of PoDIUM. I'm also the dissemination task leader for PoDIUM, and I will be moderating the webinar today. And before we get started, you can, a quick note on the interaction, you can use the Q&A box that you can see in your control panel to enter your questions throughout the presentations. However, we will collect all the questions and address them at the end. We have reserved 10 to 15 minutes for questions and answers with the speakers. Now, let me quickly walk you through today's program and introduce the speakers. Cannot see if you have your webcams open, but if you don't, please show yourselves. And yes, we will start with the project overview from Georgios Zacharopoulos. He's a colleague from ICCS, and he's the day-to-day manager of PoDIUM. He will provide a recap of the project's objectives, the overall approach, the challenges that we experienced during the project life cycle, and highlight the achievements. Then we're going to do a very good use case deep dive. We will start with the first use case, cooperative corridor management in the city of Ulm, presented by Michael Buchholz from Ulm University. And then we will move on to use case 2 that took place in Barcelona. And it's about physical and digital infrastructure for a user-centric CCAM-enabled traffic management in urban corridors with high priority vehicles and vulnerable road users, presented by Jorge Suarez from ETRA. And then we will move on to the second Spanish use case, which will look into real-time responsive PDI for CCAM-enabled traffic management in the Mediterranean cross-border corridor, which will be presented by Harry Vasiliadis from Autopistas. And we'll move on to the last two use cases from Italy. Use case 4 on trusted cooperative perception for intersection maneuver assistant and we will hear jointly by Guido Castillo from Links Foundation and Filippo Vicentiner from Stellantis CRF. And finally, we will see the use case 5 on risk management in a highway tunnel in Trento, in Italy, presented jointly again by Paolo Facin from Autostrada del Brennero and Filippo. Following the use case deep dive and concluding the webinar, we'll have Ioannis Kosmidis from Insights, who will provide an outlook and overview from the business insights and sustainability of the PoDIUM results, including the market outlook, but also a techno-economic analysis of the results. Then we will conclude with the Q&A session, as I said, where we will address all the questions. And yeah, that's all from me for now. Thank you all for joining. And Yorgos, the floor is all yours to begin the presentations.
Thank you, Sevi. Just give me 1 second to share my screen. And please let me know if you can see my slides.
Yes, if we can move
Okay.
to the first
Yes,
one.
I need to remove the
Super.
first one. Okay, thank you. So, hi, good morning, everyone. Thank you very much for attending PoDIUM's final webinar. My name is Giorgos Zacharopoulos. As I've mentioned, I'm a scientific project manager for ICCS, and for more than a year now, I have the role of the day-to-day coordinator manager, let's say, of Project PoDIUM. It's 3+ years of work now concluding, and we are here to go through all the outcomes. So PoDIUM stands for PDI Connectivity and Cooperation Enablers, Building Trust and Sustainability for CCAM. We are 26 partners from 8 different countries, with a total budget of 12 million euros, and the duration of the project was 39 months, concluding actually this month. Our goals are simple, to be honest, is to design and validate key enablers that allow vehicles, infrastructure, and digital systems to work together seamlessly, to ensure that all data exchange actions are done in a reliable and secure manner, and to enable communication amongst all relevant parties, meaning vehicle to infrastructure, vehicle to vehicle, etc., in complex environments. So, why PoDIUM really matters? Europe's transport ecosystem is evolving rapidly. Automation, connectivity, and data-driven mobility services are no longer future ambitions. We are currently in a transition phase, let's call it, and this transition depends heavily on infrastructure that is actually smarter, more connected, and more adaptable than we have today. PoDIUM actually contributes in a list of different areas. So, for example, with regards to policy, we provide policy alignment through our use cases and even through our collected experience during the development of the project. We'll discuss about that later. On standards and deployment, with regards, we have the operational architecture and standardization through development of our technology solutions that we offer. In terms of safety and efficiency, we support that through our use cases, focusing on VRU safety and traffic efficiency and real-time coordination of traffic. And lastly, with regards to scalability and sustainability, we provide that through the flexibility of the systems that we have developed, which also supports the European environmental goals. With regards to our objectives, the first one is that I have put it there in bold letters also, because I think it's the most important one, is to enable CCAM in real traffic conditions. Then we are looking also to identify and assess the enablers we have been discussing for, advance and demonstrate also physical and digital infrastructure technologies in our 3 living labs, explore system trust and data truthfulness, which is a critical factor in safety and reliability, and also to deliver a flexible reference architecture that public authorities and the industry can use to plan and implement their CCAM services. Now, how we do that? What's the methodology that we're using? So we have developed a hybrid data management architecture that combines edge computing for the development of digital twin models and for low latency decision making on the road level, and cloud services for scalability and high system trust and robustness. We also focus a lot on multi-connectivity, combining technologies such as 5G centimeter wave and 5G millimeter wave, ITSG5 and Wi-Fi to ensure that communication remains reliable and available, and of course redundant, even under challenging conditions. That's a little bit different to what other similar projects have used so far, so I'm quite proud of it. So from how we are moving to where, so we have split our work into 3 living labs, one in Germany with 1 use case, one in Spain with 2 use cases, and one more in Italy with another 2 use cases. The German Living Lab was based in the city of Ulm, where use case 1 focused on cooperative corridor management, and its demonstration was completed back in April of this year, successfully, very successfully. Then the Spanish Living Lab included 2 use cases. Use case 2 was based in the city of Barcelona and focused on urban traffic environments by creating a CCAM corridor within the city. And use case 3 was based on C32, which is a highway just outside Barcelona, and focused on creating a simulation of a CCAM cross-border corridor, let's say, and a mobility as a service solution. In our case, that is taking place between the cross-border between Spain and France. The Spanish Living Lab demonstration, both demonstrations actually were conducted last month in Barcelona, again really successfully. And lastly, the Italian Living Lab also included 2 use cases. Use case 4 that was based in the city of Turin and focused on trusted cooperative perception for intersection maneuver assistance. And lastly, use case 5 was based on the A22 of Autostrada del Brennero and focused on risk management within a highway tunnel. The Italian Living Lab demonstrations took place in October in the city of Turin, again, really successful. So, what we have achieved after 3+ years, various different things we could say. It's a really long list of things that we could say. I've just selected a few, a little bit more generic. We proved that it is feasible to demonstrate PDI technologies and, and applications in real traffic environments across 3 different places also. We developed methods for enhancing trust and reliability for ITS applications. We provided platform applications to enhance protection for VRUs. We developed a really concrete set of technical enhancements and policy recommendations. And of course, we developed a system architecture that supports vehicles and road infrastructure in communicating between them and sharing important information more efficiently. Of course, there are several other things that we achieved. We coordinated highway traffic across borders, overcoming mobile service roaming challenges. We delivered a human-machine interface for connected vehicle drivers, allowing them to be made aware of surrounding vehicles and alerts coming from the infrastructure, and so on. It's a long list, and you will hear more details about it at the use case descriptions. Of course, not everything was easy and seamless. There were challenges that we faced, starting with, let's say, the lack of unified testing for automated driving permissions across the EU countries. So our OEM within our project was coming from France, for example, and having to bring him to Spain was not an easy condition. because there was no, as we mentioned, there were not unified guidance, let's say, between the countries. On top of that, we had interlinked requirements within different countries. For example, from the ministry level, we had to also align with the requirements of the city councils. In some occasions, fortunately not many, the liaison with the associated authorities was not very clear, since there were not specific guidelines and timelines. And lastly, which I also find it quite important, is that there is no common insurance policy across all EU countries, especially for automated driving vehicles, testing for automated driving vehicles. So, where are we now? We have completed all of our demonstrations. We have completed our final event in Barcelona last month. We are sharing our results as we are doing this webinar today, and our outcomes with the wider CCAM community that will also be available, as Sevi mentioned, online later. What we still have to do is to complete and submit our last few deliverables. We are very nearly there, and based on our results, support the wider CCAM community, of course. And we are looking to also offer some knowledge transfer sessions with associated new projects, or newer than ours project at least. And yeah, liaise as much as we can with public authorities, infrastructure operators, mobility service providers, and offer the knowledge that we have gained. Lastly, I wanted to mention that there is this QR code within this slide that you can scan if you want and receive all the information that we have from the project. That means articles, videos, deliverables, presentations, anything that we have developed those 3+ years. And this is all from me, and I think we can move to the use case deep dive, and I think Mikael is following up. Mikael?
Yes.
Floor is yours. Let me stop sharing.
Can you see my screen now?
Yes.
Yes.
Great. So thanks, Georgos and Sivi, and welcome to this use case deep dive. My name is Michael Buchholz. I'm with Ulm University, and I'm presenting this on behalf of all the German Living Lab partners, which in Bosch, Nokia, University of Duisburg, Essen, and Ulm University. And first of all, I want to show you a little overview on our use case and the Living Lab. Let's start with the use case. We've divided this use case into 2 scenarios. The first scenario is that something like a big truck or could also be a construction site blocks a lane, and then only one single lane remains for the traffic in both directions. And this is what we mean by corridor management. We have this only single lane as a corridor, which has to be managed for the traffic flowing in both directions. We want to have as much as efficiency as possible and also safe passage of this obstacle on the road. And scenario 1 is managing this corridor management with with 2 connected and automated vehicles, one coming on the lane which is blocked and the other one coming on the opposite side. And what we tried to, or what one of the research goals was, and we successfully showed that it works, is that we only use perception from the vehicles, from the connected vehicles. So there's no infrastructure sensors used to achieve this goal. We have used the infrastructure as a ground truth to compare, but we could show that this is also possible with this lightweight solution with only CAV's perception, which allows for a much faster deployment of such a service. The second scenario, we exchange one of the CAVs by a vulnerable road user. In our case, it's a bicyclist, and the bicyclist is connected to the edge server via a smartphone app. And now the goal is not longer efficiency of the traffic flow, but it's more on safety, because we want to guarantee the bicyclist a safe passage along the obstacle, so that the bicyclist can safely pass the obstacle and come back to it to the own lane before the CAV passes. For this, because this bicyclist doesn't have any perception sensors, we use the infrastructure sensors for sure. To give you a little overview, Georgos already showed that our living lab is in the city of Ulm in Germany. Here, if you close a look, it's a suburban area. It's called Leer. It's a suburban village which belongs to the city of Ulm. And at this intersection, we have some infrastructure sensors on extra poles, but also on light poles, which are along the street. And you see some camera, some images that show the test site. I want to now come to the main technical contributions. First, summarized on some slides. In the end, you will also see a video showing our corridor management, which was recorded during live operation in real traffic. So it was on public roads with real traffic. First of all, an overview on the functional components. We already talked about the connected and automated vehicles. They for sure need the automated driving stack, which was already available before the project in the vehicles, and they can transmit their own position and in the CAM message, also the CPM message for their perception. And if you have a bicyclist, the bicyclist uses the VAM, vulnerable road user awareness message, instead of the CAM for its own position. On the other side, we have the infrastructure sensors, which are only used in the ground truth baseline solution and in the scenario 2. And then our main part was on the interconnection between the road users and the edge server on the communication part, and also on the functions on the edge server, where we have a cooperative planner. This is the planner which is responsible for doing the corridor management, and it's connected to a digital twin. The digital twin represents all the we call it objects, so all the road users as a mathematical representation being around this area. So we have the pedestrians, the bicyclists, the vehicles, all in a mathematical model, and also how they will move. And then we can predict how the movement will be. We can detect this obstacle, and then we can plan accordingly. And we have the CITS message handling, which receives and transmits the messages from and to the road users. I said one part it was the communication. So we had multi connectivity in our test site, which comprised of different 5G networks. It was a centimeter wave 5G network, a 5G millimeter wave network, and respective antennas also on the vehicles. And we additionally had a 60 gigahertz ad hoc Wi-Fi network on the infrastructure and also on the vehicle. And now what we did was kind of like testing if we can use this multi-connectivity for, on the one hand, have more bandwidth to communicate large amounts of data in the case of function offloading, which we will be talking later on. And on the other hand, to ensure that data always receives the receiver safely, so we can also kind of multiply the messages and see that that it definitely will be received on the other side, because if at least one of the channels is available. This is again shown here. So you see this multipath scheduler for us as a user with the applications. This communication layer was completely transparent, and the scheduler was doing the scheduling between the different transmission paths autonomously. So we as a user didn't see if the message runs over the 60 gigahertz ad hoc network or one of the 5G networks. This was all the functionality of the scheduler, who could be configured to either use one of those or to use all of them, depending on if you have a focus on reliability or on higher bandwidth. We had good coverage in our in our test site, even better than expected. It was also surprisingly that millimeter wave 5G worked well, although we had moving targets like the vehicles, which is not foreseen in the standardization of millimeter wave 5G. And we have shown that the scheduler can adapt easily and fast to changes in signal quality, so that we don't see any drop of messages when changes occur. In addition, we were working on the digital twin, and in this case, on the data reliability of the digital twin. So the digital twin was already available from previous projects, but we worked on making it more reliable. For example, if some false detections are reported by any of the sensors, we want to avoid to include those false detections into the digital twin. So we worked on reliability methods for data fusion and also for assessing the reliability of the different sources. We used multi-object, multi-sensor fusion based on base rules as a digital twin, and we used, for example, subjective logic as a means for doing this reliability checks. The monitoring monitored all the sources, and we could check if the statistics fit to those statistics we expected during design time. Then an additional add-on, which we did in addition, especially Bosch did in addition to what was proposed in the project, in the proposal, was that we additionally to this corridor management also worked on function offloading. Function offloading means that parts of the functionality of the automated driving stack are moved to the edge for computing reasons, for example. In the upper part of this slide, you see how today vehicles work. If they are automated, they do everything on board. So we have the sensing, the thinking, and the acting all on board the vehicles. In the original setup without infrastructure sensors, we have the vehicle sense, think, and act, but we have additionally the infrastructure sensors, part of the sensing on the edge and part of the thinking, like the maneuver planning on the edge, and then the final trajectory planning is done on the vehicle. And now this was extended by function offloading, which means that not all of the functionality is longer being calculated on board the vehicle. Parts of the sensing is moved to the edge, so we can save resources, we can do more complex computations on the edge than maybe on the limited hardware resources on board the vehicle, and also for the planning, and then the rest is again done on the vehicle. And Bosch successfully tested that also in with our setup, PoDIUM setup. But now I want to show you a video. The video is also has also sound, so it will explain again all the corridor management and will show you the results from both scenarios. Now let's start the video.
Welcome to the PoDIUM project, an EU-wide research initiative dedicated to the future of cooperative mobility. PoDIUM aims to develop and validate a cutting-edge digital platform for cooperative, connected, and automated driving. This platform will enable mobility solutions to operate safely and reliably in real-world mixed traffic environments, leveraging the edge cloud paradigm and 5G connectivity. In Europe, PoDIUM operates 3 living labs. The German Living Lab in Ulm, with partners Bosch, Ulm University, the University of Duisburg-Essen, and Nokia, tests and validates these innovative solutions directly in real urban areas, the mixed traffic environment of tomorrow. We make a crucial contribution to safe and efficient mobility. Urban mixed traffic is complex with diverse road users from cars to pedestrians. The challenge: varied connectivity levels. Some connect optimally to our edge cloud, others only via smartphone or not at all. This unpredictability makes urban traffic demanding. Not all road users are connected to the cloud, and many areas lack the necessary infrastructure technology. How can cooperative traffic management effectively optimize safety and traffic flow in such mixed traffic? Road obstacles often create challenging and dangerous traffic situations, especially with lane reductions. We will show how our edge cloud support and cooperative strategies can resolve these efficiently and safely. Our core message: edge cloud supported cooperative traffic management operates precisely and reliably in complex mixed traffic, even without additional infrastructure sensor technology. Let's see our solution in action. First, a classic overtaking maneuver, Vehicle 1 blocks the lane. Our connected Vehicle 2 approaches and detects the obstruction. However, oncoming traffic blocks the opposite lane, making a simple, uncoordinated bypass impossible. Corridor management is crucial in such dynamic situations for smooth and safe movement. No infrastructure sensor technology is required, all necessary information is supplied by the vehicles themselves. This scenario involves 3 participants. Stationary Vehicle 1 is unconnected. Our connected Vehicle 2 aims to overtake. The oncoming Vehicle 3, also connected, coordinates with the cloud, providing its local environmental model. Without our system, this complex situation would lead to stagnation, uncertainty, and a high risk of collision. The German Living Labs solution diffuses highly dynamic traffic situations. We utilize high-performance edge cloud computing and modern wireless communication. Our system relies purely on vehicle sensor technology. External infrastructure sensors are not required. Vehicles 2 and 3 send their pre-processed environmental data to the edge cloud, where it's merged into a detailed environmental model. Our edge cloud fusion algorithm continuously verifies its assumptions. This ensures the environmental model's robustness and reliability for safety-critical applications. For maximum performance and availability, we integrate the latest radio technology, 5G centimeter wave, 5G millimeter wave, and 60 GHz Wi-Fi ensure extremely fast and reliable communication. Our specially equipped vehicles use multi-connectivity. This ensures continuous, high-speed communication, even under challenging conditions. We developed innovative methods, including an intelligent scheduler from the University of Duisburg-Essen. It optimizes radio channel handling, significantly increasing system reliability. If a vehicle lacks sufficient onboard computing capacity for complex functions, calculations can be flexibly performed in the edge cloud. We call this function offloading. Our system successfully resolves this dangerous situation. Vehicle 2 is safely guided to the opposite lane, and oncoming Vehicle 3 is precisely prompted to stop, enabling the maneuver and ensuring safety. This system works in the real world. Our video demonstration impressively proves its practical application. Now, to another aspect of mixed traffic, vulnerable road users. Cooperative management is more complex here, as vulnerable road users are typically unconnected. Without our system, the cyclist would wait long or risk bypassing the obstacle. Our system, however, provides increased visibility for the cyclist. For precise cyclist detection, we combine smartphone positioning with infrastructure sensors. This creates a complete environmental picture, informing cyclists via app when the path is safe. The German Living Lab system smoothly resolves complex vulnerable road user situations. The cyclist is safely guided past the obstacle without delay, while connected vehicles optimally adjust. This system also works in real mixed traffic. Our video demonstration impressively shows the efficiency of cooperative management. As demonstrated, the PoDIUM project pioneers the future of cooperative and automated mobility. Through dedicated work at the German Living Lab and our European partners, we prove how intelligent, edge cloud-supported corridor management effectively resolves challenging traffic situations in real-world environments. This paves the way for safer, more efficient, and more sustainable transportation for everyone. Thank you.
And with that, I want to summarize the main results from use case 1. We developed a local environment model, which includes reliability checks, which is more reliable than it was before we started the project. And also a reliable multi-connectivity approach using the scheduler, which was mentioned quite often, and also tested new technologies like millimeter wave for moving targets. We were able to protect vulnerable road users in this corridor management use case by connecting them with a smartphone with the edge server and with the connected automated vehicles. And the cooperative corridor management led to improvements in traffic efficiency and also safety. And we additionally showed the complex offloading of complex functions like detection on sensor data or planning from vehicles to the edge. Some lessons that we learned. we learned that cooperative maneuvers are even possible without infrastructure support if enough connected and automated vehicles are available that submit their perceived surroundings in a CPM message. 5G millimeter wave is a viable option for connected vehicles. VRUs can be included into cooperative maneuvers, and transparent scheduling on lower level network is a good thing, but it doesn't work with ITSG5 technology. Originally, we planned to include that as well, but we saw that this technology is not ready for doing the low-level scheduling. And function offloading can support vehicles to include complex functionality without having powerful compute hardware on board. With that, I want to conclude my presentation on use case 1, and I pass over to Jorge for use case 2 from the Spanish lab test site. Thank you for your attention.
Thank you, Michael. I'm going to share my screen. I hope you can see it, right? Put in full screen. Okay.
Yes.
Good morning, everyone. So I'm Jorge Suarez from ETRA IND, and I'm going to present the results of use case 2 of the PoDIUM project. This use case focuses on physical and digital infrastructure for user-centric, CCAM-enabled traffic management in complex urban corridors, with focusing on high-priority vehicles and vulnerable road users. These are the partners that have participated in all the activities within the use case 2. Our testing took place at the heart of Barcelona, specifically in the Gran Via corridor. This is a highly complex and dynamic environment with multi-lane traffic, emergency corridors, public transport, and complex intersections. We focused on 3 core scenarios. First one is about prioritizing emergency vehicles while at the same time coordinating cooperative maneuvers for connected and automated vehicles. In a scenario 2, we optimized the traffic flow using real-time data, but also using a digital twin and sending alerts to the connected and automated vehicles. And on the third scenario, we tried to protect vulnerable road users in case of there was a risk of collision by sending detection warnings to the vehicles, but also to the VRUs. These are the vehicles that were involved in use case 2, a connected vehicle provided by IDIADA, a firefighter's truck from the Barcelona Fire Service, a connected and automated vehicle provided by Mila, and finally a bicycle from the Barcelona Bicycle Sharing Service. Moving to the results, well, as this webinar is focused on the results, we start with the platform, which contains a group of services that has been deployed in both the cloud and in the MEC. So these services communicate with the infrastructure, the vehicles, the roadside units, and the cameras that have been installed on the road through hybrid communication, 5G and CV2X PC5. So the system demonstrated good robustness. We achieved 100% of service availability through our testing. And in terms of communication reliability, we successfully transmitted over 64,000 CAM and DNM messages via this hybrid architecture or communication, and thus achieving a success rate of 95%. In terms of latencies, we can distinguish between 3 stages of communication. First of all, from the moment that the CAM message is created by the vehicle until it is received and recorded by the infrastructure deployed in the MEC, the average latency is around 155 milliseconds. Secondly, from the moment that the DNM message is first published in the MEC until it is received and validated by the vehicle, the average latency is around 215 milliseconds. And thirdly, from the moment that the hazard is detected and until the denim is ready for the delivery in the MEC. Excluding transport latencies, the average latency is around 57 milliseconds. So well, this is well within, and this is our within our safety thresholds. But we identified that future optimizations in the MEC and the 5G quality of service configurations could reduce these latencies. Moving to scenario 1 related to the priority of emergency vehicles. In this scenario, we have replaced the traditional time prognosis method that is currently used by the Barcelona's traffic management. We have replaced it with real-time GNSS positioning of the vehicle to prioritize along the vehicles around the corridors. So the emergency vehicle is sending its position every 2 seconds through a CAM message. You can see here 2 graphics. On the left, it is on the baseline, which is the prognosis time, where we detected some intersection in which the emergency vehicle was not passing with green. And on the right side, with the PDI support, we detected that the emergency vehicle passed in green phase along all the intersections of the corridor. So the results were good. We show a 51% of increase in the number of times that the emergency vehicle is finding the green light along the corridor. This reduced the response times for the firefighter service. On the other hand, we also reduce the impact on surrounding traffic by optimizing the work times, which are the safety intervals that between the traffic light changes to make sure that the emergency vehicle finds green along the intersections. So as you can see in the picture on the left, the time interval to let the emergency vehicle pass through the intersection can be optimized, as shown between the blue and the pink lines. And this allows more time for the green phase at the crossing streets, so that we can improve the traffic flow along these crossing streets. The results were also positive. We achieved a 53% in reduction in the traffic disruption compared to the baseline. And finally, beyond these traffic lights, we tested how the infrastructure can help to clear the path to the emergency vehicle. So we successfully performed cooperative maneuvers where connected vehicles received the warnings through the DNM messages to move aside and to clear the path to the emergency vehicle. We achieved a 100% of success rate in these maneuvers. Now here it is a short video about these maneuvers. Here the emergency vehicle is approaching the connected vehicle, then it receives the DNM messages and moves to the lane aside. Now the view from inside the vehicle, the connected vehicle is waiting. Now it receives the DNM message and moves to the other lane, so that the emergency vehicle can pass through. Okay, this is all for scenario 1. Now moving to scenario 2, where we have demonstrated the power of urban digital twin by using the data from connected vehicles. So the traffic management system was able to generate accurate origin and destination matrices and real-time travel time warning analytics. Sorry. This could be very useful, in our opinion, for the traffic management. We analyzed the number of trips which were correctly processed by the traffic management system. In terms of origin and destination data, 95% of trips were fine, and for the travel times data, it was 94% of successfully trips. So the failure causes were due the GPS accuracy, 50%, but also due to the current digital model that is already installed in the traffic management center in Barcelona. So in the end, after this traffic analytics, this allowed the manager, the traffic management, to detect incidents and reroute traffic dynamically, so improving the overall efficiency and in the urban grid. These are the dashboards of the smart mobility platform, which has been updated. On the left side, you can see the travel times per road segments. And on the right side, the arches representing the origin and destination of the vehicles. Then, based on these traffic analytics, we can detect if there is an incident along the vehicle's routes and send them a DNM message so that they can change their routes. Now here, another short video. Well, here the initial route of the vehicle, and then it receives the DNM message. Now, because there is a congestion along the corridor, so that it can move to another route. Okay. Now our final scenario was focused on the most vulnerable road users. So using an AI-based video processing from the infrastructure cameras, the system successfully detected potential collisions between the vehicles and the VRUs. You can see here the infrastructure that has been installed at the intersection, the cameras, the roadside unit, and a cabinet over a traffic controller, which contains the router and the video analytics processor. Here I have a short video to show the vulnerable road user, well, the road users detection, but also the estimation of their trajectories, so that we can estimate if there is a risk of collision between the vehicles and the vulnerable road users. Well, this longer, so I can move now to the next slide. So the impact on safety was measurable with CV2X warnings via DNM messages. I mean, we detect the road users, we estimated the traffic, the risk of collisions, and we sent messages to the vehicles and warnings to the VRU. We are used through an app. We showed that the reaction time to a potential collision was increased. This was tested in this case with the connected vehicles in Barcelona. So showing an increase in the distance to collision from 27 to 39 meters. So increasing the margin of safety. So in other words, the braking starts earlier with the CV2X warning through a DNM message to the drivers. And in addition, we observed a shift from hard braking to soft braking. So the deceleration intensity decreased from an average 3.3 to 2.2 meters by square seconds. So it represents somehow a 33% of reduction that makes the maneuver safer and comfortable. Again, a short video from inside the vehicle, which is here you can see the HMI provided by the ADA. So it receives the DNM. Here it is the VRU. And on the other side, the VRU receives a warning through the app. To conclude some conclusions. So use case 2 has successfully proven that a hybrid 5G and CV2X communication can be effectively supported by 3 CCAM services in a dense urban environment like the one in Barcelona. However, there is a margin of improvement in low latencies through the MEC optimization and a better quality of service configuration of the 5G network. We have increased the traffic light priority for the emergency vehicles For that, at least we need the position of the vehicles, the emergency vehicles, every 2 seconds for an effective priority. We also enabled traffic analytics in a dense urban area, allowing traffic optimization and vehicles to change their routes. For that, we need for HD maps to improve the digital twin accuracy in urban corridors. It was also detected. And we also achieved increases in the safety margins for VRU protection. Of course, we tested it complex intersection in Barcelona, but it is very dependent on the specific configuration of the intersection, but also on the traffic regulation, the traffic lights and priorities and so on. Well, and finally, as a recommendation for the European Commission, to be honest, this was mentioned by Yorgos in his presentation, we think that more harmonization of regulatory permits is necessary for autonomous driving tests. And that's all from my side. Thank you for your attention. I'm happy to take any questions, and I give the floor now to Harris. He will present the use case 3.
Thank you, Jorge. Hello, everyone. I will share my screen. All right, so use case 3 is about real-time responsive PDI, physical and digital infrastructure for CCAM-enabled traffic management in highways. So the use case 3 main goal is to look at cross-border highway corridors, ensure smooth and safe traffic, and using, of course, physical and digital infrastructure, as we said, which we wanted to work in real time and in a responsive manner, leveraging a CCAM environment. So we had 2 scenarios. The first scenario is daily cross-border commuting, and the second one is about safety critical incidents. Both scenarios stress the same platform under very different operational conditions and uses a few different vehicles and different functionalities that were tested. Use case 3 was implemented and tested on a real 12-kilometer highway. And this is basically the C32 highway near Barcelona. And the idea that the highway, is part of the Abertis Autopistas Future Road Lab as a test bed for innovative technologies. This is not a closed lab, but it's a real operational environment with real constraints, real vehicles, traffic conditions, etc. The physical and digital infrastructure in use case 3 combines not just the connected vehicles, as well, but also 5G nodes, RSUs, roadside units, that means, and traffic cameras into a single responsive PDI. I will focus only on the elements that are essential in this case, but you can read on the right side more. The main messages that we used in use case 3 was CCAM, location messages, DNM for alerts, EVIM for traffic strategies like speed limit, MCM for the rest of traffic strategies like, for example, blocked lanes, as well as CPMs, BAMs for vulnerable road users, and MAPMs. I will present briefly just some ideas of what we tested. So we had 3 main situations that we looked at in this, especially in scenario 2. Situation 1 is an incident that happens before the cross-border area. The second one is on the cross-border area. And the third one is across the border. Okay, just to give you an example, I'll focus on situation 2. Which provides an interesting problem. There is a 5G cutoff zone right on the border. So when you're crossing the border, you're passing from one operator to the other because you're roaming. with your mobile phone, for example. Therefore, you don't have any 5G connection. So therefore, messages that perhaps are sent by the vehicles are not being received by the 5G network. So what we did is we installed RSUs, roadside units, with EC5 technology in order to be able to capture these messages and transfer them to the TMC, what we call it, the Traffic Management Center on the edge. In turn, the Traffic Management Center detects that a vehicle has a problem and then launches the relevant strategies to the rest of the vehicles, as you can see on the lower side of the screen to the right. Therefore, they know that they have to reduce the speed, they have to avoid, for example, the right lane because there is a stopped vehicle there, etc. In terms of cross-border connectivity, cross-border roaming, of course, as we said, is dealt in the way we introduced with the RSUs that cover the border area. But also we had an issue. What happens if an incident happens on one side of the border and you need to communicate it to the vehicles that are on the other side of the border? Each side of the border is managed not just by different 5G networks, but also by different highway operators. Therefore, they have a different system, a different TMC, a traffic management center. So we exchange a set of specific, let's say, minimal set of data between the TMCs on each side of the border so that they can know that A, there is an incident, and B, what kind of traffic strategies are being applied on each side so they can harmonize. MEC services on the edge included, as you can see, the traffic management that we already mentioned, the digital twin of the highway, the CATS message and user handling, as well as risk management services, especially related to VRU and vehicles collision risks. The MEC services enable low latency message handling, as well as very fast processing because we work with an edge cloud, which is located, in the same, let's say, general area within Spain it can be, rather than using cloud services that are far away and therefore have higher latency. These services are basically what make the platform responsive in real time. In terms of end users, we have the driver and the operator. Highway operators, as you can see on the right side, can visualize the actual traffic status, hazards, and the actual strategies in real time. The drivers on the left side receive actionable recommendations via the human-machine interface. So basically it's a tablet screen and not just information. So both are essential for fast and safe reactions in critical situations. On the other side, we had VRU and passenger apps that can be used by individuals. The VRUs on the right side receive real-time collision risk alerts based on their relative position to connected vehicles, while on the left side, the passengers of the on-demand service in scenario 1, as we mentioned, can use the on-demand service app to interact with the automated shuttle service that we demonstrated in the project, completing the end-to-end CCAM use case as such. We had two main objectives in terms of results, technical, let's say, achievements. One was, how do you deal with the transmission of CATS messages over 5G networks? That's because the process is not standardized and it does not support broadcasting. Therefore, sending individual CATS messages would be the way to go, but that quickly becomes inefficient and not scalable as the number of vehicles increases on the highway, connected vehicles, that is. So our approach, we explore two complementary approaches, as you can see, to address the scalability. One is topic-based message distribution, and the other one is per vehicle connections. This allowed us to balance scalability, relevance of information, and the ability to personalize messages based on the vehicle concept. Furthermore, we worked on awareness. Awareness in CCAM is about detecting neighboring vehicles, so that is implemented via CAM messages. Instead of flooding vehicles with cams, though, awareness is compacted and distributed efficiently via CPM messages, and also customized to the location of the vehicles. So you only package CPMs in the CPM, the vehicles that are around the target vehicle that you're sending the CPM to. And this, of course, as you can imagine, significantly improves scalability and relevance of information. Final demonstrations for use case 3 took place from one side in Barcelona, as we said, in the Avertis Future Road Lab. For scenario 2, the safety critical situations. And in scenario 1, the on-demand service, as well as testing how automated vehicles like the Mila shuttle that you can see in the picture respond to CATS messages. We tested it at the UTAC circuit in Paris. The final results in general were very positive. We achieved pretty much all the KPIs. The service end-to-end time was well below our target, reaching below 1.5 seconds to go from vehicle to the mech to the vehicle. And the cross-border interruption time was about 54 seconds. Also, we expected higher, about double that. But it should be noted that these were experimental 5G networks and not commercial networks. In real networks, this is expected to be even lower. The CAV, the shuttle speed was achieved at close to 80 kilometers per hour, 72 to be exact, in full AD mode, SAE level 4, which is quite an achievement considering that there aren't that many SAE 4 vehicles on the roads, and even less on a highway environment. Traffic strategies implementation was tested. From one side, as we said, the CAV responded perfectly, and within, let's say, under 5 seconds to complete a maneuver that was dictated by the CATS messages. On the human driver side, the results varied, and we achieved from 3 to 5 seconds minimum response time to complete the maneuver, all the way up to 16-30 seconds, but this can depend a lot, the variability, apart from perhaps some measurement errors, can depend on driver attention as well as traffic conditions. We recommend further work on UX, UI, and driver interaction design to improve this human-machine interface in the vehicle. So as we said, to conclude, all key KPIs were achieved or exceeded, and these results show that responsive cross-border PDI for CCAM is not theoretical, it is deployable today, delivering real benefits to highway users and operators. Thank you for your attention. I'll be happy to take your questions afterwards. And for the next use case, we have use case 4 and Guido.
Thank you, Harry. Do you see my presentation? Do you hear me?
All good.
Okay.
Yes.
Well, thank you. Well, these are all the Italian partners. Let me introduce just one slide to introduce the use case 4. This has been a very challenging use case it is developed on a single cross point, and the goal of this use case is to provide timely information to the vehicle produced by different sensors. even infrastructure sensors such as cameras, lidars, and also the infrastructure information from traffic lights. And the goal is to fuse all this information using also vehicle sensors and information provided by the users themselves with the VRU app. And so to help the autonomous vehicle to use the cross point by protecting vulnerable road users that are continuously using this cross point. This is a very crowded cross point, and it was challenging from this point of view. This is in brief how it works, since the information is collected in digital twin from cameras, from the users, from vehicles, from traffic lights, and it's fused. And the goal is to produce timely, more accurate and trustable information to the vehicle to perform the maneuvers. And the VIMA application can use this information to give warnings to the vehicle. Okay, just a brief overview of the results that we have reached in this use case. Well, these are the technological achievements. The trust computing basis behavior of an onboard unit. So an onboard unit that behaves as a trust computing according to standards. So that can be verified periodically in order to avoid attacks to their integrity. So their software is continuously monitored in order to avoid attacks to its integrity, to avoid the programs to be changed, and to guarantee that the onboard unit as a source of information is trustable. And on the other hand, the truthfulness concept, which is to allow redundancy and the information provided to the vehicle by allowing different sources of information, producing CPMs with a higher perception quality. So as more information, more sources of information are available, the CPMs produced are few, because the vehicle would receive a single set of CPMs with a higher quality. It's different from receiving all CPMs from all other vehicles, which would be more efficient. Another outcome of this use case is the use of a VRU application, which is can be used as a navigation application for vulnerable road users, such as bicycle users or pedestrians. It can be used in both cases, and we have developed also a bicycle hardware specifically for in order to increase the positioning of the bicycles in the test site. We will see afterwards a KPI specifically that talks about the position of the positioning. Okay, this a brief of a screenshot of one of the outcomes, which is a real-time CPM visualizer that we developed in order to analyze the development of the traffic in real time, because every second the situation changes. So it's better to have a panoramic view of what the system is perceiving, and what the information present in the digital twin. On the other side, on the KPI side, we obtain 58 centimeters as the limit of the precision of the position solutions we have on the vehicle. We are using mass market hardware, so with RTK corrections and internal sensor fusion, we reach this goal. So we are satisfied of the result, since around this test site is characterized by urban canyons. Just only in the cross point, it's almost open sky. So we reached this 58 centimeters by measuring the semi-major axis. We can see that we have monitored from the cams produced by the vehicle. In every cam, the semi-major axis is produced. So we have reached and very satisfied with this goal. Also, we have noticed that it has been enough precision for this kind of application, and we will see later result a couple of slides after. Regarding the latency, it is very low in the sense that the 5G network provides very low times. If we use ICMP, we have 13 milliseconds of one-way time delay. In transmitting the complete CCAM message, we stay below 60 milliseconds. So it's very well below the limits we have for the reaction time allowed for this kind of applications in order to send warnings or update the information into the edge infrastructure that we are using. On the other hand, is another product of this. This is not exactly a KPI, but we use the positioning of the vehicle in order to calibrate the CPM precision, the CPM sensor. So the rosette unit is focusing the vehicle while it's passing by in the cross point, and we use the position of the vehicle to check the CPM position of the object detected with the vehicle position, and we realized that it has a median of 1 meter. But this is a completely expected result, since the detection can be made from different angles of the vehicle, and the position declared by the vehicle is in where the position of the antenna is located. So we were expecting this offset, since the camera perceives one of the faces of the vehicle while it's passing by. So we are satisfied of the precision of the particular on the detection and also on the positioning of the vehicle. From the vehicle point of view, I leave the floor to Filippo to continue with the presentation.
Yeah, thank you. You can see my screen?
Yes.
Yes.
Okay. Yeah, so let me go next slide. Concerning the vehicle, we demonstrated what happens at the intersection thanks to the assistance by the road infrastructure. So we have an enhanced awareness because VRUs are detected, so their presence can be injected on board the vehicle system beyond the sensor range, and this is of paramount importance to avoid accidents with other vehicles and vulnerable road users. We can give preventive warnings to the drivers, and also we can give maneuver assistance in the sense of recommendation on when to pass the intersection. That can be translated into manual driving recommendation for enhanced awareness of the driver itself, or into automated maneuvers. Indeed, we installed the PoDIUM components, the V2X onboard unit by Lynx, as well as our automated driving prototyping PC coupled with the control computer on the demonstrator. Here you see the installation in the trunk of the car. Of course, this is not a production installation, it's a prototype by which we can receive messages through the V2X OBU. These messages are translated into virtual objects that are fed into the PoDIUM ECU. In the PoDIUM ECU, there happens the data fusion, and then the data fusion translates into recommendation to the driver, or potentially not tested in the public roads, but potentially they could control longitudinally and laterally the vehicle. This is one of the KPIs that is most relevant for us. It's the enhanced awareness when approaching an intersection. We had presented this in January as preliminary results, and we are happy to confirm then over multiple trials. So in January, we produced a partial results showing how the coverage by collective perception can outperform the coverage of awareness of just the onboard sensors, not because the onboard sensors are lacking in performance, but because their field of view is limited or can be hindered by the presence of other vehicles. And as a matter of fact, what we experienced in the center of Torino is really a crowded situation, where the vehicle approaching the intersection is often in the middle of the traffic, with vehicles passing quickly or slowly, and also it's crowded areas, as Guido explained, full of pedestrians that can suddenly cross the intersection in a violation, in a queue, etc., etc. Thanks to the CPM, you can see that in the range, let's say, of 30 meters, we can have almost full coverage of the pedestrian detection, receiving constantly the CPMs by the infrastructure. It is to be said that we feed the onboard system not with all the CPMs, but with the CPMs that are relevant to the trajectory of the vehicle. On the other hand, you see the sensor, the average over the multiple trials of approaches. They show a decrease in the availability of information to the automated driving system already at 20 meters. And beyond the 40 meters, we see that we still can get some advanced information. So even when we are far away from the infrastructure, we can already have a sense of the presence of the VRU, while the onboard sensors still don't detect the presence of the pedestrians in this case. So in summary, the main outcomes, I'm also resuming the part of Guido. The main outcomes from this use case 4 is an infrastructure-based awareness and assistance systems based on a digital twin and a dedicated intersection movement assist application that provides collective perception data, warnings, and recommendation to the automated vehicles and the driver. We have seen an onboard communicated unit dedicated to CITS message exchange with the infrastructure, but also with trust computing capabilities. That's really one of the novelties of this project for us to test. Precise positioning strategies. You have seen the results on sub-meter localization capabilities, and onboard applications performing the data fusion of V2X and sensors. And it's to be highlighted here that we fuse V2X data that are coming from a trusted platform with a digital twin. So it's the trust is really high. to provide enhanced awareness of especially vulnerable road users. The main recommendation is that we should complement in the future these outstanding outcomes we gotten from the PoDIUM infrastructure in Torino. We need to complement and test them in a closed track to address controlled crossing by the vulnerable road users, because during the Living Lab there was really a crowded situation where vulnerable road users kept on crossing the intersection. Okay, thank you. I give over the floor to Paolo for use case 5.
Hello to everybody. Let me share the screen first. Okay, you should see now.
Yes.
Yes.
Let me start. I am Paolo Faccina. I am the CITS manager for Autostrade at Brennero. So my role is to be able to make the CITS system up and running, mostly. And let's start with the preamble of why this use case is important from the road perspective inside. Because we tackle the problem of tunnels. We want to do a risk assessment on tunnels, so detecting real-time situation and warn the drivers. Why? Why tunnels? Because they are one of the most dangerous part of the network. And because from the driver perspective, you have no space to maneuver because you are in a tunnel. And from the road operator perspective, it's a dangerous situation because when something happens, you have a compounding effect on traffic, and moreover, the assistance and rescue are very difficult. So we want to avoid as much as possible to have accident nearby the tunnels. The good fact that this use case allows us to transcend the tunnel settings, because the risk assessment module we thought that we saw that it could be scalable to any dangerous stretch of the road. So tunnels is very interesting, but you can apply this setting in any stretch of the road that you deem problematic as a road operator or as a city council or road network manager. Our pilot site was the Tash Tunnel, located north to the Bolzano. We installed the infrastructure to be able to create the risk assessment module, and we monitor both direction. It is a good pilot site because it has a very high traffic load, and also we have a very limited emergency access. So it's a real setting where this risk assessment modules is very useful. What the scenario is about? You get automatic vehicles that approaches the tunnel, and they need to get a real-time hazard denim message to be warned about possible danger. And then, using this information that comes from the infrastructure, the vehicles adopt cooperative adaptive cruise control and act according to the risk message they received. And moreover, they need to perform cooperative perception, exchanging CPM between each other. What is the key focus on this scenario that could have been done everywhere? That's the tunnel. We want also to provide a continuous position, or at least provide enough information to cars to self-localize, because for automating driving settings, the self-localization of the vehicles is very important. Otherwise, he cannot interact with the information he gets and can leads to wrong decision. And as well, all we know in tunnels, you get at best inaccurate GPS position, or in the worst case scenario, you get no GPS at all. So to address this scenario, we have a lot of technical challenges that needed to be addressed. And the first one was to create a real-time detection system, which is a high-level technical stuff, as you can see, as you saw on the use case 4. Then we have to integrate this system, this information, with the existing CITS system that our highways is operating. Moreover, you need to face the challenge about the GPS position, so you have to give at least some information on position to the cars, to the automatic vehicles and connected vehicles. And then from the car perspective side, they needed to do data fusion, getting information from all the from their sensors and the infrastructure to do the cooperative maneuver necessary to avoid the risk situations. To do that, we have to install a lot of equipment. There was something related to position, let's call it some anchor that gives signals to say to help cars to self-localize. So at least they get some static point of reference where they can use to address their relative position. Of course, we have the CITS system, so equipment to broadcast the messages that warns the vehicles of dangers. And then there is the risk assessment equipment, which is the camera, the LiDAR sensors, of course, other roadside unit, and then all the GPU and AI model to compute the risk level in real time. And then there is the part where it is the data fusion, who feeds on all the sensor data from the risk assessment module and the CITS platform that counts vehicle, determines a risk assessment, and then produce a warning to drivers. So the flow is there is a data collection phase from the infrastructure point. So from vehicles and infrastructure, you get also the information from sensor and the CITS system. The risk assessment module computes in real time the risk level, and if deemed necessary, it produces a warning, a CITS message, or refine an existing one, and then it sends to the automatic driver. And this is, of course, a continuous monitoring. It dynamically updates the risk level as new vehicles arrives nearby the tunnel. Of course, this is seems just a technical part. It was a lot of technical work to make it work, because each system I showed, this installation is a separate tool that we can use. The big hurdle was to make the system not only talk to each other, but really be really integrated with each other. I don't need only the risk management flow to provide me message, but this message needs to be available to my CITS system and then broadcast to the car. And then last, something about the positioning challenge. Of course, as I say, the self-localization is very important for vehicles. So without it, no CITS message makes sense for the car. And if the car cannot correctly interpret the CITS message, they risk to do some, there are safety risks because you get the misleading event localization. So the car believes that there is a risk nearby when in fact is 50 meters ahead. So that's a problem. How we could taste that? We do not only do tests on the pilot site, but we do also in a test track where we were able to test a separate part of our PoDIUM chain of the risk assessment using CITS, the GPS positioning tool that could help drivers, and the integration with the CITS system. We did a lot of tests with very good results, and the last question was, does the whole chain works? Because we tested separately each use case, each maneuver, each component of the system. Yes, it has been done. We did a test on November on the pilot site, testing the complete chain. So the car was able to travel through the tunnels, receive the updated message from the PoDIUM platform. And from the infrastructure point of view, all pieces communicated together. But to know whether this information were enough from the driver perspective, I will leave the floor to my colleague Filippo from Stellantis. Thank you very much.
Filippo, if you speak, we cannot hear you. You're muted.
Okay, sorry. Okay, share my, okay. Can you see the presentation now?
Yes.
Okay. What do the vehicles need to have in this use case? They have to have a submitted positioning capabilities that work inside the tunnel. So their positioning is integrated with a data reckoning system based on a data fusion with the onboard sensors and also with the V2I exchange of ranging messages to the roadside units in order to obtain the relative position. They are equipped with ADAS and automated driving functions that were tested up to level 2 in the public road, but the availability, they are capable of going up to level 3 and give the availability of level 4 automated driving awareness system, not actuation of level 4 control, but awareness system. So SAE level 4 perception and operational design domain information. The scenarios are cooperative ACC, whereby there is an event sent by the roadside unit Paolo mentioned, for instance, roadworks with the closure of one lane, and the vehicles, for instance, they cooperate to enable the cut-in by an equipped vehicle, a connected vehicle, and then the CAV follows the connected vehicle through cooperative ACC. So its target speed becomes the speed of the vehicle in front, not only thanks to sensors, but also thanks to the exchanged cooperative awareness message CAMS. And also the target speed limit gets limited by the speed limit within the construction site. We also are testing the level 4 perception. The concept is that if a vehicle follows in cooperative ACC another vehicle and the connected vehicle in front exchanges messages about its perceptions, messages, for instance, of a queue of vehicles starting, the vehicle behind can remain in level 4 automated driving as long as there are safety situations, as long as the positioning capabilities of its own are satisfied in terms of level 4 positioning KPI, which is of the order of 20 centimeters. And also if there are no interference by additional vehicles that are not equipped. For instance, a vehicle that inserts within the two cars, the connected vehicle in front and the CAV behind, would make the level 4 capabilities of the car behind not available any longer because it exits the operational design domain. So again, a collective perception, like in the previous use case 4, also in use case 5 is of paramount importance to extend the perception of the vehicle. And the main outcomes here for us was the capability, was the possibility to develop ourselves a module sending cooperative perception messages based on off-the-shelves V2X components and in ETSI standards, so enable an interoperable sensor sharing between vehicles. We tested this in multiple trials along the highway, both in tunnels and outside the tunnels, to address the problems of collective perception accuracy. So how accurate are these messages based on the detection of the vehicle in front? How are they dependent on the positioning quality of the vehicle in front and of the host vehicle that has to do data fusion between its own sensed object and the detected object by the vehicle in front? So positioning plays a key role. We obtained, so the target as a reference was 20 centimeter. We obtained in general between 10 and 30 centimeters. Not so good as we had expected in open sky, but we have to consider that the Autostrada del Brennero is in the middle of the mountains. Sometimes we have narrow valleys. So as a whole, taking the average and the distribution functions, we are below 30 instead of 20, but a positioning solution worked fine in the scenarios considered during the pilot. We also investigated the extended perception, and the target was to have a matching error between the objects of the sensors of the host vehicle of the CAV and the objects gotten from the car in front through the CPM. They have to match, otherwise the CAV doesn't know if the object detected, if the same object is detected from the vehicle in front and from the ego vehicle, the two objects have to match. If they don't match in position, we have a missed tracking of the object because the object is seen as two. So the target was that these corner cases should be less than 10%, and indeed this was achieved. We also lowered in simulation the frequency of the CPM based on actual data. We simply undersampled the actual data to lower the frequency of the CPM received. And we also found an interesting result that should be confirmed in further studies, that 3 Hertz as a lowered frequency is a kind of threshold above which we have more than 10% mismatch of the objects. So if the CPM from the vehicle in front are received less at a lesser frequency than 3 Hertz, we have a risk of mismatching the objects with the camera detection of our vehicle. So the main outcomes as a whole is a precise in-tunnel vehicle positioning system, ensuring accurate navigation and automated control. So we said the results as an order of magnitude is below 30 centimeters. We have anticipated, we could benefit of anticipated information for CAV based on the real-time tunnel risk levels assessed by the system presented by Paolo. That has also risk management strategies that can trigger automated response for lane changes or speed adjustment for instance, in the cooperative ACC use case. We developed a vehicle-based collective perception based on an interoperable ETSI standard, and we could integrate all the V2I information, V2V information with the own sensors data for cooperative ACC and SAE level 4 perception for checking when level 4 could be available in tunnel scenarios. In general, the recommendation is, I didn't speak very much on the V2I trilateration system because the results were not so satisfactory, and we combined the V2I trilateration system with the dead reckoning to obtain the 30 centimeters. So the trilateration we found together with Autostrada del Brennero that is highly dependent on the relative position of the roadside units, and the latter is limited by the characteristic of the tunnel. So a triangle results always in a very narrow triangle, not a very widespread triangle, because we are in a linear environment, in a linear shape environment. And this is a limitation. Further study should be performed on the CPM because of course the results they depend intrinsically. Also, the results we had on the matching between sensors and CPM depends on the characteristics of the sensors of our prototype. So further studies should be addressed with different data fusion systems and different sensors to consolidate the results. Thank you.
Thank you, Filippo. And Ioannis, let's conclude with your presentation.
Yes. Good morning to all. My name is Ioannis Negosmidis from Insights Consulting, and today I will present you the business insights and sustainability of PoDIUM results, an overview about the objectives of the business activity, the methodology we used for the techno-economic analysis, an overview and a description of the business model of an indicative use case 1, some assumptions and rules used for the techno-economic analysis, the results, and a comparative analysis and recommendations for all the use cases. So our objectives were to identify the economic opportunities and sustainable business models for new actors like SMEs, as well as existing actors investing in new CCAM services. So we had to propose a set of promising value networks for each of these 5 use cases, including all the actors, their relationships, revenue streams, etc., and also to propose some business models using the business model canvas methodology for each of these models. And finally, to evaluate the sustainability of the proposed models based using a techno-economic analysis. This is the methodology we used in order to estimate the cost of deployment, operation, and maintenance, as well as the revenues of the different use cases. We use the dimensioning methodology in order to estimate the number of required components, a price evolution model based on learning curves in order to estimate the evolution of the prices of the different components based on their maturity. And we also model the operating and maintenance expenses. So about the cost estimation, the first step was to create a shopping list for each of the study years, taking into account, of course, equipment replacement. Then using the required number of components along with their prices to estimate the capex. Then we estimated operation, administration, and maintenance expenses, including personnel cost, maintenance, connectivity, and hosting service cost, installation, and decommissioning. And finally, we also added an overhead, including contracting, insurances, tax consultancy, etc., and ensure also the profitability of our cases. Regarding the business model of use case 1 as an indicative use case, the owner who exploits in reality the outcomes, the platform, the main beneficiary is a startup company with a core team of at least 8 essential members, developing and providing also the services of use case 1. The main customers are construction companies or the public authorities. The value proposition is to enhance, of course, the safety and traffic management at cities where roads are blocked. And the revenue stream is based on selling the management services for such road segments. And the cost structure includes personnel cost, operation, maintenance, installation, capex, etc. Some assumptions and rules. We have a weighted average cost of capital of 10%. The starting year is 2026. We have a study period of 8 years. Percentage of taxes, almost 16%. Overheads, 12.5%. And the service tariff, the price that we are providing, we are selling our services, is 52,435 euros, which was derived using the cost-based pricing methodology. We have also taken into account the inflation ratio rate, mainly for personnel cost, using some figures and forecasts from IMF. Then we had some more assumptions and rules regarding the personnel cost. As we mentioned at the beginning, we assume that we need at least 8 full-time equivalent positions in order to run this startup company, including development personnel, product management, business development, marketing, technical support, and operations manager. This startup team is able to handle, let's say, 40 up to 40 road sites. And then a growth in fixed cost of 6,000 euro per newly added line segment was also assumed. Some assumptions and rules about OPEX. We have connectivity cost of 250 euros with an annual erosion of 5%. Due to the maturity of this, let's say, of OPEX. We have some part about storage processing costs, which is 850 per line segment. About maintenance, 500 euros per segment, and about installation and decommissioning, 10,000 each. About the capex, we need one SIM card per line segment, 100 euros, with a lifetime 11 years. We need 4 AI traffic cameras, 2,000 euros each, and 4 lidars and radars with price 1,000 euros each. As mentioned before, we use the learning curve methodology in order to assess the price evolution for the components, based, as we can see, on their maturity. So since AI cameras are less mature, we are expecting that their price will drop faster. We then estimate the required number of components per year, and then by multiplying with their prices, we estimated the capex, the investment needed annually. And we can see that the biggest part of our investment is coming from the AI cameras, followed by the lidars and the radars. A similar approach for the OPEX, and as we can see, personnel cost along with maintenance are the main contributors of OPEX expenses. Then we try to draft, let's say, to design a sales plan in order to estimate the revenues. So we assume that in the first year we will have 10 line segments, second 2025, and at the last year we will have 185 line segments with revenues almost 10 million euros. So by combining all these results, we derived the cash flows and then 3 main indices: the net present value, which is about 2 million euros, the internal rate of return 25%, and the payback period of about 6 years. Then we performed also a sensitivity analysis in order to identify the most critical parameter, which, as shown in this slide, is the price of the services. So we can see that by increasing the price by 60%, let's say, The NPV will increase of about 10 million euros. Focusing on the price, we performed more sensitivity analysis on the cash balance, the cumulative cash flow, and we can see that we should keep the price not below the initial estimated price in order to have a positive cash balance and also a profitable case. We followed the same calculations for all the use cases, and we derived this comparative, let's say, table. And as we can see, some comments or conclusions. Let's say that use cases related to high-risk locations with clearly defined operators, such as intersections and tunnels, achieve stronger and faster financial performance. Since these markets have already established procurement mechanism, regulatory requirements, and high willingness to pay for safety improvements. On the other hand, use cases that depend on widespread adoption of connected vehicles, like use case 1 and 2 at the apologies, at the citywide scale, are facing slower monetization, although they are offering significant societal benefits. And use case 3 is in the middle of the two cases. So use case 1 and 5 emerges as the most attractive purely from economic perspective, since they have the biggest, let's say, NPVs. Use case 4 demonstrates the lowest investment risk due to the highest internal rate of return. Use case 3 offers the best balance between growth and scalability. And finally, use case 2 is the use case that depends more on the technology adoption, and its success is closely connected with the penetration of connected vehicles and the willingness of cities to integrate these technologies. I think this was my last slide. Thank you very much. I'm at your disposal for questions.
Thank you so much, Ioannis, and thank you to all the speakers for your presentations and your contributions here and so far. We are very well over the schedule, and thank you for joining, for staying until now. Let me just share my screen very quickly. I'll do that after. As I mentioned in the Q&A box, I suggest, I know we are way over time, but I suggest we take 1 or 2 questions. There is already one question from Panagiotis Patazopoulos, an ICCS colleague. It has 2 aspects. I assume this goes to the Italian partners. Panagiotis is asking if you explored any trade-offs related to the trusted computing enable OBU. Is that a question for the Italian partners? I think so, correct?
Yes. If Guido, I think, can take this question since links developed.
Yes.
Please.
Well, I'm not sure if I understand exactly the intention of the question, but we faced the problem of the trust computing basis as also an onboard unit problem, because we need that the onboard unit to be even protected against hack attacks, against their integrity, so that the software might be changing during the operation. And that is the mechanism that we adopted to put the onboard unit to behave as a trust computing base by the means of an attestation protocol that allows the external entity present on the MEC services to validate or sorry, to perform the attestation, periodical attestation of the onboard unit as a source of information. In the case that the attestation is negative, the onboard unit is not able to publish information into the main broker present on the system because it is would be not allowed to produce other messages. So this is the main mechanism that we have implemented in PoDIUM to implement the trust mechanism into the use case 4. I'm not sure if it answers the question for the user.
Panayoti, I will unmute you in case you want to share anything.
Can you hear me?
Yes.
All right. Okay. Well, thanks, Guido. Yes. Yeah. Essentially, I was asking whether you have any sort of dynamic relation between the attestation and the operation of the OBU, meaning that in case you assumed, or in case you enforced, let's say you asked for increased guarantees, that will give you some sort of a penalty in the reaction of the OBU, meaning that it cannot be able to take over both the attestation computation and also, meet the stringent requirements for sending out some CPM, CAM, or whatever. That was a question. But as far as I understand, the approach was a little bit different, right? You just checked whether the attestation is fulfilled in order for the OBU to be enabled. Okay, all right. Thank you. That's clear.
Yeah, thank you.
Thank you, Panayoti, for the question. Thank you, Guido. Keeping an eye on the time, I suggest we're half an hour overtime. So as I mentioned in the Q&A box, if you have any questions, you can feel free to send it my way, and I'll be more than happy to pass it on to the speakers, and we can follow up in writing. Before we sign off, just very quickly to share my screen so we can show you. I hope you can see it. So I hope you can see it.
Yes, sorry.
Okay, just a very quick note. Our final brochure is all ready and will be shared and launched later today. So please keep an eye on our platforms. As Yorgos mentioned in the beginning, we have this QR code which opens the full world of PoDIUM. So feel free to scan it, and you can find all the information regarding the project. And with this, I want to thank you once more for joining this webinar, for staying this far along. The recording of the webinar will be uploaded on our YouTube channel, so you'll have the chance to come back to it. And again, if any questions arise, you can email me to follow up later on. And yeah. A big thank you once again to the speakers, and thank you to everyone who joined for PoDIUM's final webinar, and everyone has been here since the beginning. It has been a great opportunity, a great journey so far to work with you, and yeah, thank you.
Thank you very much, Sevi.
Thank
Thanks,
you.
everyone.
Thank you.
Thank you.
Sevi.
Bye, everyone.
Thanks all.
Bye.
Bye-bye.
Thank you very
Bye.
much.
Bye.
Bye.